Okay, so this is lecture, let's see, February 14th, so 16th. All right. Last lecture, we talked about thermal strain and how that influences the deformation and internal forces in systems based on a change in temperature. Okay. And that change in temperature could be coupled with changes in forces or applied forces to a system. Okay, this time we're going to go through another example. In this example, we have a polymer cylinder. That would be the cylinder 2 in the center. It's clamped between rigid heads, okay, by steel bolts, two steel bolts, two of them, one and one there shown in the diagram. Okay, they're steel. Okay, so the modulus of elasticity for steel is 29,000 KSI. The coefficient of thermal expansion for steel is 6.5 times 10 to the negative sixth. Okay, degree per degree centigrade. And the bolts have a 1/2 inch diameter. They give us the stiffness and coefficient for our polymer cylinder and give the outside diameter of that polymer cylinder with a wall thickness, right? So this is actually a cylinder or pipe of polymer that is being clamped between two heads. They give us the distance A, okay, or the depth of our cylinder being, let me double check here. L2 is 24 inches. Okay. And then they tell us that our B dimension is 28 inches. All right. And they say the temperature of the assembly changes by 120 degrees, and they want us to determine what's the normal stress in the polymer cylinder, the normal strain in the polymer cylinder, the normal strain in the steel bolts, okay? Well, as we normally do, we'll develop our free body diagram. In this case, I'm going to cut out, right, the bottom plate of this polymer assembly so that we can essentially look at, well, what's going on with our forces applied to that bottom plate. Well, we might have a force in the bolt, right? A force in the polymer, and then another force in the bolt. Well, due to symmetry, as you can imagine here, right? We could have three different forces. We could sum moments, and we could figure out that the force in the top bolt is the same as the force in the bottom bolt, right? We always need coordinate systems, so I'm going to give us coordinate systems so that we can do some of the forces in the x. That would be the only equation that we need. Some of the forces in the x is 0. Well, that means 0 is 2 times F1 plus F2, right? Well, what does that do for us? Well, we have two unknowns in one equation, right? And if we have two unknowns in one equation, we're going to want to relate our deformation, right? Well, we know that this is a closed system. So if the rods get longer, right, then our polymer cylinder needs to get longer. If we look at our, what we'd call our compatibility equations, which relate force and deformation, then we would have the deformation in 1 equals the deformation in 2. So our deformation equals the force times the length over the area times the modulus of elasticity, right? Plus our coefficient of thermal expansion times the change in temperature times the length, right? So that would be our deformation equation that incorporates, right, our mechanical strain or strain due to loads, right? Load-based strain and our thermal strain. Right? And each of our components, delta 1 and delta 2, will each have some of those components. So if we plug in those values, which is fairly tedious to do, right? We've got different coefficients, we've got different dimensions. Now, if we take that and we simplify, right? And we would want an expression for one force in terms of the other, right? That would be our goal. So I'm going to save you a lot of tears here, right? And going to tell you that if you took that big long expression here and we simplified it, we would come up with this expression like so, plus now we have our thermal strain contribution based on the area of our steel rods multiplied by thermal coefficient of expansion. Get rid of that. Alpha 1 L1 minus alpha 2 L2. We get that long gross equation for what is the force in the bolts in terms of the force in the polymer, the length of the polymer in the bolts, the areas, the stiffnesses, the change in temperatures, the coefficient of thermal expansion. All of those things will give us F1. Well, now that we have F1, we're going to substitute that back into our equilibrium equation. What does that mean? Well, sum of the forces in the X equaled 0. And that was 2 times the force in the bolts plus F2 must equal 0. Where I'm going to plug F1 into our sum of our forces in the X equation, right? From up above, that's this guy here. We're going to plug that in. Well, when we do that, we go through a even longer, tedious process, and we get the force in 2 equal to 2 delta T, area 1, modulus 1, length of the bolts, times the coefficient of the bolts, times the length of the bolts, minus coefficient of the polymer, times the length of the polymer. This is all really disgusting looking, right? Glad I just jumped to this and didn't make you guys go through this. 1 over 2, E1 over E2 plus 1, right? So all of that nasty stuff came from our equilibrium equation, right? We have that. We know that we need to develop a deformation relationship, right? Because we really have 2 equations and 3 unknowns, right? We have F1, F2, and F3, right? Well, we can use some of the moments to equate the fact that F1 equals at the top equals the 1 at the bottom, but now we only have 2 equations and 2 unknowns, right? Some of the forces in the X, 2 equations being we have now displacement. We take displacement, we plug in our load displacement plus our thermal displacement. We set those equal to each other because we know we have a closed system, and if the polymer moves, then our rods move, okay? We solve that for one of the forces. We take that equation, plug it into our equilibrium equation so we can solve for the other force, right? In terms of just our parameters or variables that describe the problem at hand. Well, if we go back now to the problem statement, they gave us all sorts of crazy information about this. Well, for one, it's going to undergo a change in temperature of 120 degrees. The area of our bolts, well, they gave us the diameter. We could figure out the area. I'm just going to give it to you. We know the length of the bolts. Well, it's 28 inches. Well, why is that? Because we have these 1.5 inch steel plates, right? That added, 2-inch steel plates, right? It was 24 inches between. Well, the bolts actually extend to the outside of the plate, so we have 28 inches for the bolts. We know that the modulus elasticity of steel is 29,000. Our coefficient of thermal expansion is 6.5 times 10 to the -6th per degree Fahrenheit. We have the area of the polymer. All right, well, we could figure that out. It's the area of that pipe. We know the outside diameter. We know the thickness. We can figure it out either go to the appendix, right, and look at our properties of areas. We would have a cylinder there, we'd have a stock equation given if you were given thickness or if you knew the outside diameter, the inside diameter. We know the length of this polymer is 24 inches. We know that the modulus of elasticity of this polymer is 370 KSI, right? That's nothing, right? We had 29,000 KSI for steel. We have 370 KSI, so this thing is like a sponge compared to the steel rods. It's not very stiff. Alpha 2, well, you have 39 times 10 to the negative 6th per degree Fahrenheit as our coefficient of thermal expansion, right? It's not only is it less stiff than our steel rods, well, it expands more, right? We have 39 versus 6.5. Well, if we went through that whole process, right, dumping in all of that information, okay, making sure that we track our units. And if we track our units properly, right, writing everything out, we would then yield an F2 of 8,890 pounds. Okay. That would be F2. Well, what does that mean? Well, that just means in our free body diagram, okay, F2 is actually pushing the other way, right? Which makes sense. If we had this polymer and we heat it up 120 degrees, right, it's going to be expanding. It's going to be expanding faster than our steel bolts are because our coefficient of thermal expansion is larger. So it's going to be pushing on this plate because the steel rods are going to be holding the plate back. It's not, the steel rods are not expanding at the same amount, right? And in doing so, that polymer is going to be providing a force or exerting a force on that steel plate. So if we go back to our equilibrium equation, we know that 2F1 plus F2 equals 0. We could say that F1 equals negative 1/2 F2. Well, if we do that, F1 now becomes 4,445 pounds, just like that. Well, now that we know forces, that long, tedious process of knowing forces, right? We really are interested in our normal stress and normal strains, okay? The stress in the polymer, but the strain in the polymer and the strain in the bolts. Well, we know that our equation for stress equals force over area. Well, in this case, right, the force in the polymer is F2, and we know A2. This would be F2 over A2, or negative 8,890 pounds all over 8.402 square inches, or negative 1,058 PSI, right? What does that mean? Well, that means that thing's in compression, right? All right. F2 is negative. Right, what's that mean? Well, it's acting in the other direction. So it actually means that, right, if the polymer is acting to the left on our steel plate, then that means the steel plate is acting on the steel polymer, or the polymer cylinder, right? So our normal force is going to be acting towards, right? So really, I won't erase it, but really F2 is acting to the left on the steel plate. Well, that means the steel plate is acting to the right on the polymer. Well, a force acting towards the surface, as we know from our sign convention for normal force, and for stresses, that means that we are in compression. Now we want to know, right, part B is, what is the strain in the polymer? Well, we have an equation for the total strain in an element equals the strain due to stress, right, plus the strain due to thermal. Well, and we know because of Hooke's law, we have the strain due to stress equals the stress over the modulus of elasticity. And we know that the thermal strain equals the coefficient of thermal expansion times the change in temperature over which the material undergoes. Well, if we plug those back into this equation, we're going to get a larger equation that states that the stress over the modulus equals alpha delta T. Well, if we plug in our values, we know the polymer, right, underwent 1058 psi in compression, or it is in compression after 120 degrees. So we're going to say negative 1058 psi, right, over, well, the modulus was only 370 ksi. Well, we have a units imbalance, so we're going to say that I have 1,000 psi per ksi plus 39 times 10 to the negative sixth per degree Fahrenheit times 120 degrees Fahrenheit. Right? What does that give us? Well, that says the strain total equals 0.00182 inches per inch. And lastly, if we go through the same procedure, where we have our total strain equal to our strain due to stress plus our strain due to thermal. All right. Well, we know the force in the bolts, right, was 4,445. We're going to say that our strain total equals 4,445. It was positive, so our force is positive. It's in here, I'll write this out. So this is kind of misleading of where you may have gotten this. So we know the strain due to stress is stress over over E, right? The modulus of elasticity. Well, we know the stress is the force over area. Well, we didn't calculate the stress previously, right? In part A, they just asked for the stress in the polymer. They didn't ask for the stress in the steel bolts. So if we took this, combine these two, we could say that the strain is equal to the force over the area times the modulus of elasticity. So in that case, right, if we plugged in F over AE, we know that the area of the bolts is 0.196 inches squared times 29,000 KSI. We know we got to do some conversions for units. I'm going to multiply by 1,000. Then I'm going to plus coefficient, right, times 10 to the sixth, times the change in temperature. We get a total strain equal to 0.0015 inches per inch. And that is that example. And that completes our axial section, okay, chapter 5 in our textbook, okay. So now we're going to go through, I want to make sure, chapter 5 in the textbook. So we had chapter 1, stress, chapter 2, strain, chapter 3, material properties, right? That's where we get Hooke's law, that's where we get proportional limit, that's where we get the modulus of elasticity, all of those things. We talked about design a little bit, right? Factors of safety and how that can integrate into our designs. We have allowable stresses, we have failure stresses, and we have factors of safety, right? Factors of safety are there to help us select, design components so that we are able to honestly sleep at night, right? We have some uncertainty. Engineering is just a big educated guess. And the more educated we can be about a subject or some sort of design, the lower that factor of safety can be, right? Aircraft is a big example of that. Lower factor of safety allows them to make lighter aircraft. Lighter aircraft get off the ground easier, more cost effective, more efficient, right? Versus if we're going to build a building, right, those factors of safety are likely higher. There's a lot more uncertainties, a lot of different skills of labor, different time frame, different locations on the planet. And so those factors of safety can go up. So that was chapter 4, and then we drove into chapter 5, and as you guys have done in the homeworks, and we'll do in the homework that I just gave last Thursday. Let's do this coming Thursday. Is this idea of axial systems, right? Indeterminate and determinate axial systems, and how do we figure out what our internal forces are, right? That's the whole mechanics behind what we've been doing to make sure we have adequate strength. Also allows us to figure out what our displacements are. And so we've just finished up chapter 5, right? And we're going to jump into chapter 16. While we're here. We're going to kind of make this big jump from chapter 5. We're moving 9 chapters, and we're going to go to columns. Okay. Columns in chapter 16. Well, in their simplest form, I think everyone simplest form. Really, a column is a long, straight, prismatic bar or member. Oops. Subjected to compressive axial loads, right? So if I was an MET, I'd be getting super excited about this picture here, right? Incredible, okay? My brother works at Bressler as a mechanic, automotive technician, and they have a series of these 3 jacks, and they can roll these things around the shop or out in the parking lot, and they connect via Bluetooth and your phone, and you literally get them up underneath the tires, and they will synchronize themselves so that they pick up the vehicle, or in this case a bus, evenly, and you can wheel them around. Well, the jack tower here, right, is a long, straight, prismatic bar subjected to an axial compressive load, right? The tire is going to have some sort of reaction on it that's acting on these arms, which granted would put a moment on this column, but in a general sense, right, these towers are going to have to resist some axial load, right? On the CET side, well, any building that you guys are driving around Bozeman or larger cities, okay, across the country, right? Posts and beams, or this post and beam support method, is super, super common, where you have these discrete members that pick up smaller or accessory members and transfer all of that load. And then columns are these kind of vertical load transferring mechanisms, right? They provide the ability to, say, pick up the ground level, right? If in your house right now, if you're listening to me blab on, you're sitting on a floor system that likely has some sort of plywood member that then spans to floor joists or beams, and those floor joists will then span to girders or walls, or if in the case of girders, those girders are then extend to these column members, right, that then take that vertical load out of our beams and bring them down to the foundation, where ultimately they're resisted, right? So this is our CET example. Well, there's a lot of things, design considerations with columns, but there's one phenomenon that is very, very common with respect to design, and that is the tendency or the ability for a column, because they are such long, straight, and prismatic members, and they have compression, they have this capability of buckling. So buckling is the sudden, large deformation of a structure due to a slight increase of an existing load. So sudden large deformation of a structure due to a slight increase of an existing load. Okay. Could be a bad deal, right? So it's sudden. We don't like to hear that. Large. We don't like to hear that either, right? Large deformation seems like it could create a lot of damage. Sudden means there's not a lot of warning, right? So it happens out of nowhere. We don't like that either. So when we look at buckling, it's really a stability failure because it's sudden. So if we look at a ball, right, in a dish, for instance, right, and you were to displace that ball slightly one way or the other, okay, in that dish, and you let go of that ball is going to slide back down into the bottom of the dish, right? So if we did a very small, that's what dx is, right, a small disturbance of the ball, this would be what we would call a stable condition, where a small action produces a small effect. Okay. Right? We move the ball a small distance, that ball moves a small distance back, right? Stable. Unstable, well, as you can imagine, opposite, right? A small action produces a large effect, right? If we were to move this ball a small distance off to the side, say you're sitting, you flip the bowl over, set it on the countertop, and then you take the ball and set it on the bottom of the bowl and let it displace, right? If you move that ball slightly off the very top of that bowl, right, and you let it go, that small action that you imposed on that ball is going to create a large effect, right? The ball's going to roll away. So a small action produces a large effect. Well, there's one more situation here. We call it neutral. Okay. You can be stable, you can be unstable. We could also be neutral. Well, neutral would be like if you sat on a flat surface, right, a countertop, and it was perfectly flat, right? Perfectly flat, okay? And you took your ball and you moved it that small distance off to the side, right? And you set it there. It's not going to move, right? Small action produces no effect if it's neutral. The ball doesn't need to roll back. It's not forced to roll back due to conservation of energy or anything else. It just sits. Okay. Well, if we go back to these long, straight prismatic bars or members, right? Well, long, slender columns, load and compression will buckle before the maximum normal stress in the material is reached. Okay. Buckling occurs when a system becomes relatively unstable based on the compressive load. A slight disturbance causes the column to bend. Right? We haven't really talked about bending yet, but we can apply the equation to calculate maximum or critical load that could induce buckling. Okay. So if we have this ideal column, if we look at it idealistically, right? So we have this ideal column, it has a length L, an axial load P, right? And that load that we have is less than, the load that we apply is less than what we would call this P critical, right? Well, what's that? That's the ideal column, right? If the load P is right at P critical, okay, or what we would call the buckling load, the column buckles slightly, right? Buckled column in a neutral equilibrium. It's just sitting there buckled, right? And if we looked at that free body diagram, right, cut out that column, we would have the applied force P, right? Applied force P, we'd have this applied perpendicular load, By, right? That's a pin. This is a pin. We'd have a resistive, right? Ace of Y and an ace of X, okay? And then we could look at a free body diagram of the partial column. So we'll just cut this column out and look at what's going on. Well, if we have some sort of bending in there, we're going to have some moment, we're going to have an axial load, and then we're going to have our axial load at the bottom. We know that some of the forces in the y of this diagram C gives us that AX equals P, right? So we're going to have P sitting at the bottom. Well, if we have P axial load vertically, we're going to have P axial load vertically at the top, right? Some of the forces in the y. And so what happened is Euler, who's a big deal in mathematics, okay? Did a lot of crazy stuff, all right? What he did is he solved the differential equation for buckling. So he did all this for us. He went through the derivation of taking a straight prismatic member, putting in a small displacement v sub x, summing moments, figuring out how those forces vary throughout the height, figuring out what the differential equation for buckling is. And when he solved it, he got that this critical load is what we call n squared y squared EI over L squared, okay? And what does that mean? Well, this is the solution for a pinned column with n modes of buckling. Well, n nodes of buckling we'll get to in a second, okay? And what did he do? Well, he made this solution for this idealized, what we call the ideal column solution, right? Ideal being that it's pin, right? So he did the solution for what we would call an ideal column, right? And I know we would call this ideal. Well, we use this ideal column in the real world all the time, okay? Like CETs and METs, if you go out there in the real world, okay, and you look at design of, even if it was a camper shell with aluminum tubing, okay, or CET side, if you're building a multi-story steel structure, right, and there's columns and beams, a lot of times the designers of those things look at those columns as ideal columns. They assume that even though you might think that there's some resistance to rotation, right, we can idealize them as pinned. So what does that mean? Well, that means we can get a critical stress, right, being our force over area, or P critical over area. What does that mean? Well, for the idealized column, that's pi squared E over what we call LR squared, right? Well, how does this vary? Right? Well, if we looked at a graph and we graphed the length of our column, or with respect to stress, the length over what we call the radius of gyration, small r. So we have P critical over phi critical, or there's sigma critical, right? So if we had, and I wouldn't say over, it's a misrepresentation here. So if we have P critical, or if we were looking at the stress critical, right? So it's either P critical versus L, sigma critical versus L over R, right? Our capacity, right? P critical or is going to do something like this, right? It's going to do something like this. So as we reduce our length of our column, right, the tendency to buckle is also reduced, right? And it's reduced drastically, right? And it's increased drastically or reduced drastically, right? And somewhere in here, we're going to have the yield stress, right? So if we were looking at the critical stress versus L over R, right? If we were getting to very, very small values of L over R, our capacity, our stress, right? Our critical stress is going to go way up to the point where it's probably going to be beyond. I guess an example of this, if you took a ruler or a yardstick, right? If you took a yardstick and you compressed it between your hands, right? That yardstick buckles very easily. Well, as you started to grab that yardstick closer, putting your hands closer and closer together, you're going to essentially grab points along this red curve. And as you got to a point, right, the capacity of that ruler really is going to come down to the capacity of the material that ruler is made out of, and it's going to yield, right, or crack or break or crush, right, before it actually buckles, right, at some distance. You can imagine if your hands were an inch apart and you were pushing a ruler together, the chances that it's going to buckle before you crush the wood or crush the steel with which the ruler is made out of, right, is very, very slim, right? You're going to crush it first before you actually buckle it. Well, if we look at some of the relationships here that this provides us, well, we could say that P critical or stress critical is inversely related to length. As our stiffness goes up, right, our modulus of elasticity goes up, well, so does our critical force or critical buckling stress, right? Well, if our moment of inertia goes up, right, well, our P critical and our critical stress goes up, right? You can't see it in this equation here, right? But it's in R. R is the radius of gyration. It's the square root of the area over the square root of the moment of inertia divided by the area. And as you can imagine, as I just mentioned, right, we have to consider the yield stress, but it's not within this function, right? So not a function of the yield stress. So the buckling stress is not a function of the yield stress, and we could calculate a buckling stress that was greater than the yield stress. So as I mentioned, right, in this original Euler's solution, we have this N term here where N is the modes of buckling. Well, if we look at this figure on the left, right, so we have an undefined column, it's pinned, right, and we look at a force P. When we got to the critical buckling load at a N equal to 1, we would get this first mode of buckling, right? It just deflects from one support point to the other. That'd be like taking your yardstick or your ruler, pushing it between your hands, and seeing the curvature of that ruler as it buckled out. Well, if you had it doesn't happen very often, but if you had certain conditions, you might have a inability to get the second buckling mode, okay, or N equals 2. Well, if N equals 2, our equation becomes this, right? And our mode shape becomes what you see here, right? And so on and so on. If you went to the third mode or the fourth mode, right, you'd essentially have 3 or 4, right? In this case, we have 1 curvature, and here we have 2 curvatures, right? So if we go back and we look at critical, right, with respect to our pi, modulus elasticity, moment of inertia, right, and this length, well, it's not very effective to have a solution that's only good for our ideal column. So what did Euler do? Well, they went back and said, okay, if we have this ideal column solution, we can come back and relate that ideal solution to all the different boundary conditions, what we call boundary conditions or support conditions for each of our columns, right? So we have our P critical now becomes pi squared EI over KL squared, right? where KL equals what we call L sub E, or the effective length. Okay. Well, how does that work? Well, what we were effectively doing is coming up with this K value, right, that allows us to establish or reestablish, right, what the boundary conditions of this column are. So if we look at our pin case, look at our pin case, we have a K of 1. Well, if we input a K of 1 into that, our PCR equation, right, or P critical equation, well, it looks very close to our first mode of our Euler buckling ideal column, right? Which it is. That's exactly what this is. It's an ideal column. Well, if we look at a fixed pin column, we have a K of 0.7. Well, we have a K of 0.7 because if you looked at the buckled shape of a fixed pin column, right? So the bottom of this column is fixed in rotation, right? And in translation. The top is just fixed in translation, right? It can't move side to side, right? Out of the page, okay? It can move up and down, but side to side and out of the page. So when it buckles, the buckled shape you would get looks something like this. And how they relate that back to Euler's equation is they say, okay, well, what is the length over which we get the same buckled shape, right? So over here we have this nice curvature, single curvature of this individual buckled column, right? Well, now we have this fixed portion. Well, they said that now we have this same nice single curvature, but that single curvature now exists over a distance of 0.7 L. So what do? Well, that K factor is 0.7, right? We're reducing the length of our column when we figure out the buckling load. If we reduce the length, we know if we reduce the length, right? If we go back to this curve, if we reduce the length, we're going to run up this curve. And if we run up that curve, we're going to increase capacity. So as you can imagine, as we restrain our column more, right, going from pin to a fixed pin, right, that fixed edge is going to restrain the column more. It'd be the same as if you took a yardstick or a ruler in your hands again, right, and compressed it together. Well, instead of just having your palms outright, at the ends of our ruler, one of your hands grabs the end of the ruler and holds onto it and doesn't allow it to rotate outward, right, or buckle. As you can imagine, for the same distance between your hands, the column that you held one end of, is going to be, right, have a higher capacity than the other one. So similarly, if we fixed both ends, right, that distance that we would get our original ideal column shape is reduced even further. We're down to 0.5 L. What does that do? Well, that means our K is 0.5. Okay. If we go the opposite direction, we start relieving our boundary conditions or relieving supports at the ends of our columns. We would get, for the case of a cantilever, right, we would need to go twice the distance in order to get our full curvature shape that we get with our idealized column. So what does that do to K? Well, K then it ends up being 2. Right? Well, we can relate this all back to stress, or a critical stress, pi squared E over K L over R squared, where this is what we would call our effective slenderness ratio. Effective slenderness ratio. All right. Well, in that equation, right, we have this radius of gyration I talked about. Well, that radius of gyration, as I discussed, is R, and it is the square root of I, the moment of inertia, divided by the area. Right? And our slenderness ratio, as we showed up here, is our KL, right, or our effective length, L sub E, over R, which is KL over R. right? Which we would then pull a K out of our diagram up above, right? Depending on the fixity of our column, and then we could figure out what our slenderness ratio for our column was. Right? Well, our moment of inertia, right? I, well, as you know from statics, that varies depending on the dimensions we're looking at. So 3D world that we live in, right? So we need to look at both dimensions in the x, right? I sub x and I sub y, right? We don't need to worry about I sub z, right? We're looking cross-sectionally, right? So if we look at this column, we are going to look down at it, right? It might look like an I shape. It might look like a rectangle, but each of these directions are going to have a resistance to rotation, right? That's the moment of inertia, is our resistance. Second moment of the area, or really it's just a measure of how stiff is it in terms of rotation. Right? So if we look at this block, if their cross-section happened to be rectangular, right? I sub y is our ability to rotate about our y-axis, and I sub x, right, is our stiffness or a resistance to rotation about the x-axis. Well, if, like it shows here, h is greater than b, well, that would mean that our moment of inertia is greater in the x direction than it would be in the y direction. And if you went out to the appendix and properties of shapes, right, we know that for a rectangle, I sub x is bh cubed over 12, and that's going to be greater than hb cubed over 12, which would be I sub y, right? It's the base times the height cubed over 12. In this case, right, the h and the b's line up for our x-axis. We'd have to flip those in the y-axis because now our height becomes the b dimension and our width becomes the h dimension. Lucky for us, engineers are lazy and they have tables to help with this. Right? Also, we have the appendix in the text that'll give this to us. And I've posted some of that on D2L. Okay. So with that, I'm going to stop and I will see you guys on Friday.